Okay, so maybe it's a good time to start. Yeah, so I suspect maybe there are more people who get confused about the time. So I think previously our long talks on Monday start at 10:30, but I think there's a potential conflict with the seminar at MIT at noon. So we decided to move all the Monday talks 30 minutes earlier. So please pay attention to the talk schedule. And let's welcome Andrea talking about band topology.
Thanks for the introduction. So thank you for coming even this early in the morning. This is early by my standard. So today we'll talk about what I would call a modern solution to the whole problem of symmetry in band theory. And I've been told that I'm supposed to keep a talk pedagogical, but that would mean that the materials I try to cover will probably be quite boring for a good fraction of you. So I'll encourage you to stay awake, but don't feel guilty if you can't. So these are some of the key references. The first three papers written by me and co-authors. So they are listed as the main reference mainly because I know the content there much better than the others. And these are other contemporary works that have some overlap, but maybe from a slightly different perspective. So in particular, these two are probably compared to this one. And this one is slightly more oriented with a chemistry point of view, and this one is slightly more mathematical. So depending on your taste, you may like these other references better than the ones we've written. So also keep a table of content here, mainly to help myself remember what I'm supposed to talk. So I'll first begin by really reviewing the very basic of band theory and the notion of symmetries there. And then I will try to introduce a little bit of band topology. It's really just a very minimal degree of topology, but enough to do what I want to do. And then finally, I will try to contrast the notion of real space and momentum space insulators and explain why that's actually a pretty useful perspective. So without further ado, let's start with the first part, which is review of just band theory. And by band theory, we basically mean that we have some free fermion Hamiltonian which is symmetric under at least lattice translation. So let me write my Hamiltonian generically as sum over sites at a distance and alpha beta some indices. And I have C, let me start with this one. Something like that. So it's really a generic Hamiltonian which is quadratic in the fermion operators, and the point is that this T, which is the coupling, depends only on the distance between the two sites or the two fermions, but not the absolute coordinates. So that would just mean that you have some kind of transition invariance in the problem. And these will be local enough that you don't worry about non-local coupling and their potential effects and stuff like that. So starting with this, we know we can do Fourier transform, so you just have a rewriting of it, and that will become something like this. So this is really just a rewriting, it's just a Fourier transform, but the main point now is that I have decomposed the different k's such that you can call this one, if you like, the block Hamiltonian, which depends on k and also some internal indices. But if let your alpha runs from, or alpha beta runs from, say 1 to some n, then this will be an n by n matrix. So it's an easy problem, yes.
Do we really have two diagonals?
Oh, sorry, that's a consistent error, thanks. So if, as long as this is some finite number, which is basically always what you're doing trying to model problems, then it's a finite number and it's a finite matrix and everything is easy, kind of. So when we talk about the band of it, all we mean is just the eigenvalue of it. So you can look at the eigenvalue, if there's n by n matrix, you have n eigenvalues, and you can try to plot it as a function of k. So maybe I have something like this, say. So now that you've found the eigenvalues, you also need to know what is the physical number of electrons in your problem. And let's say you have 2 electrons per unit cell, then we know that you're supposed to think about only the two lowest bands, so that would mean your Fermi energy is something here. Then you will say, oh, now I have a band insulator, then that's fine. Or maybe you have only one electron per unit cell. Then you will be putting up to here. And this is slightly more interesting because you now get some kind of degeneracy and then you don't really get an insulator and it's some kind of semi-metal in this particular case. So you should ask the question, is this semi-metal behavior really stable or not? So the idea is that if I do have any degeneracy, that would mean that at that particular value of k, two eigenvalues of this hk is going to be exactly identical. So that's not a generic behavior. If I give you some small dimensional matrix and there's no other symmetry constraints whatsoever, then generically you expect every eigenstate to be discrete, the eigenstates to be discrete, so there's no degeneracy. So that's really the role of symmetries in this class of problem. If you don't have any symmetries, then the only interesting things will come from topology, basically. But if you do have some additional symmetries, which are really universal in any crystal, basically, then there will be some other interesting phenomenon or some additional things that we should keep track of. So let me try to run 4 exercises in terms of thinking about symmetries in band theory. So this is exercise 1. So as I said, it's really extremely pedagogical, so let me try to be very brief on these. So exercise 1 is to say, we do have some spectrum, maybe you have some two eigenstates that are identical, and we want to see why that may be stable. So let me say I start with considering only the Hamiltonian here and drop the index k. Then I just have some Hamiltonian, and I have some states, so let me say psi and phi, such that these are orthogonal, for instance, and these are eigenstates. So maybe my Hamiltonian for these two bands here is just the same eigenvalue of psi there. So this is basically the Hamiltonian right there. And now we want to ask if it's stable. So let me say I can always add a perturbation. So this is a perturbation that without any other rules, then I can just write it down. So if I do it, then I know the spectrum will become epsilon plus minus delta. Then we will split the degeneracy. So if you have any stable degeneracy in the physical system, there better be a reason why you cannot turn this on. So one possibility is this. So let's say I actually have some kind of symmetry that I would call M. Then you write it as it's a matrix here. So under this symmetry M, psi is invariant, but maybe phi picks up a -1. So if you like, you can think of it more physically. It can be something like a mirror, and this is just the mirror eigenvalue. It's positive or -1. So as long as I have these, then we can check that this term is going to pick up nothing acting on here, but pick up a -1 by this, so it's going to be negative of itself. So this would mean that delta is going to be 0. So this is just a very simple example saying why, if you have some symmetries, then maybe you can now forbid the existence of such terms. Then that can really give you some stable degeneracy. Except that I kind of lied here, because I can also add another term. So if I just do that, then this is basically the same form of this one. So it's going to respect the mirror that I've put in here. But then it's going to split the degeneracy anyway. So with this, I'm going to change it from epsilon to epsilon plus minus delta epsilon. So now you may want to ask whether this term is also disallowed, or even the presence of this term is not going to do anything. So that would all depends on basically dimensionality. Let's say I have these bands and as a function of one momentum k. This is a good symmetry along the entire line. So originally I start with this behavior. At some k naught I have a crossing. So now if I add this perturbation, all I'm going to do is to basically split this one. So I'm going to move these away by delta epsilon. But then it should be quite easy to see that even if I do that, they will basically cross against some time beta or some other momentum. So the existence of this term is in principle going to gap out your bands exactly at this original momentum. But it doesn't really do that much, it's just moving the position of the crossing. So if you're still at the same physical field, you still get a semi-metal out of it. So the important term to really kill is actually this one in this problem. Because if you have this one, then it's just scattering, there's no remaining degeneracies. So in the language of band theory, you really think of it as saying there's some label for these bands, and maybe the mirror eigenvalue is +1 here and -1 here. And if you have a +1 band and a -1 band, they come close together, then they would just cross each other, because at this point you cannot couple them because of the forbidding of this term. Okay, so that's a very pedagogical example 1. So let me do a slightly more complicated but still pedagogical example. And that is to say, let me use some more complicated spatial symmetries than just talking about a single mirror. So in particular, let me consider, say, a C3 rotation and a mirror mx. So that will flip x to -x. That's the notation here. I'm really bad at chalk, sorry. So now this is a slightly more interesting case. If you're really already familiar with things like point group and stuff like that, then you'll notice that these two will generate what is called D3, which is non-invariant. So for people who think about these things, and if you have a non-invariant group, then the fifth representation will be more than one-dimensional. And that's basically the point, but let me go through the details. So let's imagine we think about these symmetries in real space, and we want to understand what are the properties of the eigenstates or how the states will transform under these symmetries. So let me do it in some pictorial manner. So let me start with the one site. Let me say I pick it here, I put it here. So I just want to think about the transformation of these symmetries. So under C3, I'm just going to take this point and move it here. And under the mx mirror, it's going to move this point to there. So this is what I get if I start with this configuration. I do C3 and then do mirror, then I end up with this point moved to here. So now I can try to do the same exercise, but then I'll first do the mirror. So I move this point to here, and then I do my C3 rotation. Then that will move it here. So the almost trivial observation here is just that they give you different results. So that's really all the meaning of saying this is an non-invariant group. And slightly more interesting is that we can see some of these are in fact related. Let me see. If I start with this one, and I try to do a C3, I actually get this one, right? We just stare at it. So if I do C3 and mx, and then I try to do a C3 again, this is moved to there. So these are actually related. And that would mean the action here, so this is a generic point, so it's good enough to tell you what the group structure is. So that would mean if I do C3 and mx, and then C3 again, that's the same as mx. Okay. So I can also rewrite this equation and say I can apply the inverse of this one. So that would be C3 inverse, which is the same as saying you have the square of that, because the cubic of that is an identity. So this is one relation in this point group which is going to be helpful. So now let me say I give you a state. Just call that psi. And we know that under C3 you have some eigenvalue. So one option would be just identity, that's fine. Or maybe you have the third group of unity, the non-trivial third group of unity. So some plus minus I to alpha 3. So that's also allowed because the cubic of this is going to be 1. So let's say this is the transformation, or this is how the state represents C3. Then now we can ask what happens under the action of mirror. So we can say I take this state, I just apply the mirror. It may or may not be the same state. So that's the thing we want to check. So we can check it by just applying C3. So if it's the same state or if it's proportional to the original one, then you have to have the same representation or the same eigenvalue. But here, because of this rule, I can write it like this. So I know that this state is going to have a different eigenvalue under C3 compared to the original state. So that would mean they cannot be the same state. And if your Hamiltonian is actually symmetric under all these symmetries, then these two states will be degenerate. So that's another way to get you some degeneracies in the spectrum. Okay, but this is too pedagogical to go on here. I'll try to speak even faster in that case. So now let's try to put the trivial example 2 into use in a slightly more physical example 3. So example 3, we will really try to think about some physical system, and throughout the entire talk, we'll basically talk about only this setup, which is graphene or honeycomb. So let's say we try to draw the honeycomb. That's something like that. So all these are carbon sites, and we know about the center, you do have a C3 rotation. In fact, if you rotate this one by even C6, like 60 degrees, that's invariant. So if I rotate by 120 degrees, it's still invariant. So I have a C3. And also I have a mirror. We'll just flip this one. So this is real space. And now let me look at momentum space. So if I start with this real space lattice, turns out the momentum space is rotated by 90 degrees. You just try to find the lattice lattice and disregard lattice and stuff like that. And we know the interesting physics of graphene happens mostly at the K points and K prime points. So this is K. So this is a reciprocal lattice vector, so these are the same point in momentum space. And what we observe now is simply that if you take this point and do a C3 rotation about the origin, it's matched at the same point. And also a mirror is going to match it at the same point. So here we have C3 and mx being symmetries of the momentum. And now I can talk about the representation of my block states under these symmetries. And the punchline is just that if you really do the calculation, you will find that under C3 is representing, or the states here for this standard honeycomb problem is representing C3 in the representation of plus minus 2 power over 3 angular momentum, or like this type of representation. So as long as we know that piece of fact, then by this analysis we know that the mx is going to pair the two states and ensure that they have the same energy. So that's basically one way to explain the Dirac cone in graphene. So this point, you can think of it as being protected by the combination of these two. So that's really just an application of that. But it may be helpful to try to contrast this problem with something very similar. So this is a graphene. And let me try to think about hexagonal boron nitride. So for those of you who are not familiar with it, it's basically identical to graphene approximation, except that you have boron and nitrogen and boron and nitrogen, so they're alternate. So let me just draw it again. But to emphasize that they're different, I have, say, nitrogen here. And these are my boron atoms. So we see that by just going from graphene to HBN, almost nothing has changed, except that while we still have C3 symmetry, we've lost a mirror because that will map nitrogen to boron, and they're not really the same thing. So if I really do exactly the same analysis here, at K point you still have the C2 representation, which is not changed. But what is changed is that you don't have the mirror here. So in fact, you can now get a gap. Although the C3 representations will be different. So
You mean the same?
no, they're different representations. These two are different, but these two pairs are the same. That's what I meant. Yeah. So that is just saying, simply by breaking this mirror is going to kill this degeneracy here. And if I want to think about finding semi-metals, then you need to really know the symmetries because they're basically almost always stabilized by some spatial symmetries, except for more topological cases like Rao points and stuff like that. We'll get to it later.
So in this case, the mirror along the x-axis is just trivial. The
that one is still present, but then in momentum space it's going to be like this. So it's actually mapping k to k prime, right? So it's not a symmetry at this momentum. So you still have some mirror eigenvalue for states on this line, but it doesn't change your argument. So that's the last example. So we've seen that if you don't worry about topology to start with, then without any symmetries, then the problem of band theory is basically entirely trivial. So you either think about it more topologically, then you start getting Chern numbers and stuff like that, which are interesting, or you start adding more symmetries into the problem, which are there anyway if you do have some crystal. So let me now.
Excuse me.
Yes.
Suppose you don't have any point group symmetry, but you do have a translation symmetry. Whether translation symmetry can give rise to any constraint due to symmetry rather than topology.
Right. So if you only have translation, then we basically use it up by doing this Fourier transform.
Okay.
So we already block diagonalize that, and there's nothing left. But you can have cases which are very similar. Say, let's say it's a glide. So a glide is like you do a mirror, but you move by half a step. So it's basically a root of translation, because doing that twice will give you a translation.
Okay.
So that kind of non-symmetric symmetries, they can give you interesting things. But they will be fitting into this discussion, which is almost like a point group discussion.
Okay.
So the last example will be to say, now that we've talked about symmetry properties of the bands as some special points, then you can as well think about what happens if I do have some lines for which I have some symmetries, or I can have a line in which the endpoints have different symmetries compared to the line. So let me just be a bit more precise. So let me say I have a line, and here maybe I have some symmetry, G. Then if it's a symmetry of the entire line, then of course it also has to be a symmetry of the endpoints. So let's say these are, say, corners of the Brillouin zones or something like that. But what can happen is that the endpoints will have some other symmetry which is actually larger than G. So that would mean G is in general just a subgroup. So it's just a statement that if you're all lying on the same line, you always have the same, or you at least have all these symmetries. But at the endpoints, you have more symmetries than on the line. So now if you think about representations or think about the symmetries of the states, then there will be some additional conditions, which is to say whatever you have here has to be compatible with the bands here, which are also linked to the ones here. So,
Excuse me, I'm a bit confused.
yes.
Seems the endpoint have a less symmetry than the bulk. Like a translation or some reflection is broken.
Oh, that is in real space. This
Oh,
is
this is
talking
the
about
K
momentum
space.
space.
Oh, I see.
Yes.
Sorry.
Sorry, yeah, I wasn't clear about that. Yeah, so it's a momentum space. I see.
So this line endpoint can be a special K point.
Right, right. So for instance, maybe the origin or maybe the corner.
Okay.
So, so let's say now I give you some symmetry data of my bands, but I give you in such a partial manner. Then we want to do something like detective work and see if we can patch up everything. So maybe I have some 4 special momentum. Let me just label them A, B, C. And maybe at every point I can analyze all the symmetry properties. So maybe they look like this. Say, for instance. And we know that at these endpoints, maybe they actually have higher symmetries than on the line. But let's say along the line we still have some remaining symmetries. So for instance, maybe here I have a mirror. Then for any bands here, I can label them using the mirror eigenvalues. But that has to be true also at the endpoints, because this is at least a subgroup of the symmetry here. So let me say at here I can label my states, and I know they have m or mirror eigenvalues of +1, -1 here. So let me just randomly assign. Let's say there's some other mirror everywhere. Let's say something like this. And now we want to ask the question of how I can possibly patch up all these representations and get maybe a gap state at filling 2. So let's say this is the filling 2 bands that are supposed to be filled. Then we know this is a good symmetry, so if we start with a +1 here, then it's not going to change if there's no gap closing. So the only thing I can do is to take this positive one, run along this line, and I have to connect it to some other positive one. So that's fine, I have an option, I can go to this band. But if I look at this -1 band, then these are all positive. So the only option will be going up there. So I'll actually have to go up. And now this -1 can go here, this +1 can go here, for instance. And now you just basically patch it up using some rules like that. Let me say, this is not very important to get right, except that we cannot do right. So maybe something like this. So now, if I just give you partial symmetry data, so I started with giving you only the representations at the points, because I know that these are symmetries along the lines, for instance, then I can already draw the entire Venn diagram. So the point is that if you have these symmetries along the line, then you'll basically know everything about the line just by knowing the things or the data at the points. So now we can also just stare at this and say, in fact, if I just know these isolated data at the points, without really computing the band structure, I already know that there must be some gap closing. So just by knowing these isolated points, and I rule out the possibility that it's a band insulator. So if you think of it, it's a bit more non-trivial, or it's slightly non-trivial, because the actual band crossing happens somewhere and I don't really know where. And for this simple example, maybe you can tell immediately that it has to lie along A, B, and B, C. But for complicated cases, maybe it's impossible to tell where the point will really sit, except for the statement that you can never find any insulator just by the data at the points. So that's one observation. The other observation is that if I give you basically the same set of representations, let me not redraw it, not do it, but just to say, if for some reasons I can actually exchange these two states, so maybe I just change the energetics, or maybe it's a slightly different compound, then the system is slightly different, and these two are now inverted, then I can actually undo this crossing, and then it becomes like that. So now I can get a band insulator just by exchanging these two states. So the punchline here is that if you know about the symmetry representations at the high symmetry points, and that's really telling you almost everything you want to know about these kind of degeneracies. But it's actually going to tell you even a little bit more, but or even things like topological insulators. But to see that, we need some more preparation. So at this point, let's just stick with the statements, or let's stick with the question of whether I can get an insulator at all or not at a given building, given these data. So, or the other way to think about it is to say, if I give you some symmetry group or some symmetry setting, I know there are some possible representations at different points. Then we want to ask, what are all the possible ways to connect them up in the band structure, such that you get a band gap, for instance. So let me call it the band symmetry problem. So, and this is a very old problem. It's from at least Wagner 1936. So they basically ask a question of, if I have this space group, then what are all the ways to connect up, or what's the minimal way to connect the bands to get an insulator? And even back then, they have basically a full solution. But the full solution is to say, you look at one particular setting, and you just compute all these representations, which is doable with all these finite groups. And you look at how they have to be patched up just by relations, like if this is -1, it has to go to -1, something like that. So you basically have a standard recipe that you can use to analyze any group or any space group. But that recipe itself is not very efficient in the sense that you need someone to sit down and do all this computation and then think in their head whether they connect it up that way or not. And if you haven't tried that exercise, then I can tell you my personal experience because I did. And for a moderately complicated three-dimensional group, it's extremely cumbersome. It will exhaust my patience. So the rest of this talk is basically the thing you get when you exhaust your patience, which is that you try to find some slightly more efficient method to solve the same problem. So But this is, I would say, is a full solution if you have the patience. If you really can sit down, and there are not many groups that you should worry about. There are only 230 space groups and 1,651 magnetic space groups. But this is included in that, so that was almost like cheating. So if you think about magnetic space group anyway, there's only 1,651 cases to consider. So if you use that solution, you can use it on all these, then you can solve the problem. But let's try to do it in a slightly different manner. So here comes the second part, which is to say, let's try to introduce a little bit of band topology. But it's really just a little bit because I don't think I know anything beyond that. So the idea is to say, now for this, for the time being here, let me just not think only about representations, but also about the eigenstates of the Hamiltonian. And let's say I have some band structures like that, and my filling is here. And I want to think about the ground state of the system as just filling all these states, which is below the Fermi energy. So one way to say that is that at every momentum, I have some block state, maybe labeled at 1 and 2. So my many-body ground state for this free fermion problem is fully characterized by the set of all the wave functions that I filled. So it's going to be, say, and K will be any momentum in the Brion zone. So this is, in a way, all the data about your system or your band insulator. And of course, you can start taking this and then go to some limits, say maybe infinite field bands and so on and so forth. Then you can talk about the topology of these kind of objects. But let me not do that. I will just do it in a very bird's eye view or very general manner. So let's say we want to imagine the deformation of my Hamiltonian H to some H2. The condition is just that I don't break any symmetries and I still have a band gap. And under this, I will just take my psi to some psi 2. So this is a small deformation that is a small deformation of the states, or every state is here. And these two are basically smoothly connected, or they are, in whatever ways you want to sharply define it, they are basically connected or deformable to each other. So now imagine I actually get some kind of topological invariant, let me say index of it, and I wouldn't try to prove anything, but I believe you can believe me that these will be the same. So if you have a small perturbation to Hamiltonian and maintains that gap, doesn't break any symmetries, if you evaluate your topological index here and there, they will be the same. What is more important is that if you have some other set of states, so let's say I now have two different insulators, just want to compare them. I can put them into the same space, I can evaluate all these indexes, and at the end of the day, just find that they're different. As long as they're different, then you know that they cannot be connected by these kind of deformations. So that's the only thing I need to use about topological invariance here. So to recap, the key points or the key lessons I want to tease out here is that first, the topological invariants are things that do not change under small perturbation. And second, we've already seen some very trivial class of topological invariants, which are these kind of representations. So remember, if I give you a gap here, let's say I do have a gap band structure. Something like this. Then as long as I maintain this gap, then there's no way for me to change any of these data. Of course, I can actually exchange them within the set of field bands. That's fine. But there's no way for me to go from, say, having a positive 1 and a negative 1 to another state with both positive 1. So the notion of symmetry representation of your set of field bands is already a topological invariant defined in this sense. It may not be the most interesting one in that you don't even need to know the full set of wave functions. You just need to know about it at some isolated points. But in any case, they are topological invariants. So the punchline here is that if you think about representations in these kind of more topological perspective, you actually greatly simplify your problem. So let's see how. So let's start with maybe a more conventional perspective. If you've ever looked at any old band structure calculation, then what they usually show you is some band diagram, and then you have some momentum, and they call it delta. And if whoever computed that cares about representation, what they usually do is that they say, oh, this point here, the representation is delta 1. Maybe this is delta 2, and that is delta 3. And maybe I have a bit more states, so I also have a delta 2 here, something like that. So usually if you look at these band diagrams, they care about representations, they label it this way. And let's say I also have some kappa, and I have some states. Maybe like that. Then remember our band symmetry problem is to ask how you can possibly connect them and whether you can get any band gap at some field or not. So in the old way of thinking, what you do is really just look at it and try to connect it according to whatever rules you have. But now let's try to do it slightly more topologically. And let's say I have the knowledge that this is my field length. So I'm only going to talk about the states that field or that lie below this Fermi energy. So I have basically 3 bands that field. Then remember here we never really talk about the energetics within the set of field bands. So I don't really care about how they are ordered within my set. So to me, it doesn't matter if delta 1 is above delta 2 or not. So in the original way of labeling, I've given you more information than you need. So in fact, I don't need to worry about the ordering. Then when you have a collection of things and you don't worry about ordering, then the only thing you do is to count. So here I can say, my set of field bands, I have 3 possible representations, and delta 1, 2, 3. So I would just say, as far as I care, here I just know that I have 1 delta 1 representation, 1 delta 2 representation, and none of the delta 3. So this is a way to simplify your description of the symmetry representations. The only thing I've done is to say, let's forget about the detailed energetics within the set of field bands, which doesn't really do that much to our discussions here anyway. So I can do the same for kappa, and let's say I have n kappa 1 and kappa 2. And it's just counting, so I have 2 copies of that and 1 copy of that. So far so good. Then now we need to know also how these representations relate to each other. But that question has nothing to do with my actual band structure. It's just about how maybe along this line of a mirror and how the mirror eigenvalues hash out. So let's say for more space. So let's say what I know is that for delta 1, I have some mirror eigenvalue which is +1 -1. And for delta 2, or delta 2, and this is say +1, and delta 3 is going to be -1. So kappa, maybe kappa 1 is just -1, and kappa 2 is just +1. Does that work? Maybe. Let's see. So if this is all I know, then we know that if you start with delta 1, which has a +1 -1, and you run it from delta to kappa, then you must end up with 1 copy of delta 1 and 1 copy of delta 2, just because of the matching of the content of the mirror eigenvalues. And same here, if you start with n copies of delta 2, then you must also, or at least get n copies of kappa 2. And same here. So basically the point is that the representation at kappa is actually fully determined by the representations at delta. So in the equations, let me be slightly clearer. Then I know that n kappa 1 will be -1, so I have 1 copy here. This is maybe slightly more technical. Should I explain it again, or is it all good?
So which one now has a higher symmetry?
This is higher symmetry, that's it. So the statement is that the things at higher symmetry determines everything with lower symmetry. So this is not really an independent variable. So it's fully determined by some combination of the representation of delta. So this is nothing but to say that we want to draw lines and say you connect -1 to -1, positive 1 to positive 1. It's just a more algebraic way to say the same thing. So we are trying to say, if I know everything that's happening at delta, then that fully determines the things that can happen at kappa, just because there's a lower symmetry that's connected to it. And in particular, the relations are like this, because any copy of kappa 1 here, which is -1, it must come from delta 1 or delta 3. And they come in this particular ratio, like 1 to 1, because they each have one copy of this one. And the same for kappa 2, so it must come from here and there. Therefore, it's just a sum of these two. So we've basically done exactly the same analysis, except that we try to say you don't worry about the ordering of the states, and all you care will be basically some counting. And then you reduce the notion of how they must be compatible into some kind of linear equations. That's really all we've done. Then it's really the same analysis, just that it's slightly more systematic. And now we can try to ask if there's any band gap here. So we can do it by just checking the numbers. So n kappa 1 here is 2. And I have delta 1, so that's 1. Delta 3, I don't have any, so that's 0. So this is not the same as that. And this cannot be satisfied, basically. And you can try to do the same for kappa 2. So this is 1 plus 1, so that is 2. So they are equal to each other. So if I look at actually the diagrams here, actually the Venn diagrams here, if I remember the labeling, then this is maybe +1 or -1 going to a kappa 1. That is fine. This is a +1 going to some kappa 2. That is fine. Delta 2 has to go to some kappa 2, but I don't have any kappa 2 here, so I can only go up, for instance. So, well, if you like, these will generically anti-cross. It doesn't really matter. But the point is that there must be something going above my Fermi energy. So this is what you would have concluded if you use the old method. Here I'm just giving you a slightly more algebraic way to see all these by saying you just do some counting. And then you reduce all the relations into some linear equations, and then you just check if the linear equations are satisfied or not. Is that clear? Okay. So now if you're convinced that this is the same calculation as we've done in the old method, then we can now start to say what is really more efficient about this way of thinking. So the punchline is that these are just some linear equations. So I have some linear equations, I can think of it as a system of equations, and we call it some C. So the rules will be as follows. Okay. So for any pair of matter, so if I have any pair of connected high symmetry momenta, something like say this delta kappa there, then I have some linear equations. So I just have some C, say K0, K1. And then I should start 0. So the connection of high symmetry momenta. So I take a connection of all high symmetry momenta, and then for any pair which are connected by some high symmetry line, for instance, then you'll get some linear equations. And from here, I get some set of integers which are just telling me how many states or what are the representations for the field states. So now I have some n, which is something like n delta 1, n delta 2, n kappa 1, and A2, for instance. So I just collect all the counting of my representations at all the high symmetry points. And I want to subject it to this set of linear equation. So I just ask if C n is 0 or not.
So those n are actually number of irreducible representation at a particular high symmetry point.
Right, exactly. So yeah, that's exactly what it is. So if you like, you can think of it as the range of representation. then you just take the abelian part of it, and that's just these integers.
Question.
Yes.
So what do you mean by connected high symmetry momentum?
Right, so I just mean that if you, so these are not very clearly defined here. But I'm just trying to tease out the flavor of how it's done. But some statement here is that maybe these are high symmetry momentum, isolated, and they are points only, and they're connected by some lines, which also has some symmetry.
But isn't it true that any high symmetry pair of high symmetry points are connected? So
Right.
you're suggesting something like they're high symmetry
so-
points not connected, or?
Right, so let me go to this graphene example. And let's say I again have this mirror and C3. So these 2 points, K and K prime, they are connected in that they have a mirror MX going from this point to that point.
Right.
But then this line here doesn't have any symmetry, does it?
So
Actually, it has some mirror symmetry. Yeah, so probably graphene is a bad example.
But you know, if you just draw a straight line, there are some like little group of that a straight line.
Right. Yeah, right.
It may be small, but isn't it true that for any pair of connected, like any pair of high symmetry point, I can claim they're connected.
Right, exactly. So when I say if the little group along that line is only translation and nothing else, so you really just have the momentum which is diagonalized, and there's no constraint of any sort.
I see. So
Except for the same number of bands. That's one constraint if you like. So you just have to say, oh, I have the same number of bands that are filled. That's one constraint. But except for that, there's nothing special. So you don't really need to worry about that kind of pairs. But if you have pairs that are like going from here to there, so along this line, instead of just translation, also have a mirror, then you have some constraints of that sort. Because you need to match the mirror eigenvalues here and there.
Right. Another question. So you only pay attention to these lines. So what about the high symmetry surfaces?
Right. So for the planes, they always contain lines and they always contain points, right? So at the end of the day, if you know a good set of points, then that's good enough. So if you have just a plane and then you can take some representative points.
Maybe the question may be, so suppose you have some irrep,
right.
Say along high symmetry points and high symmetry lines,
Yes.
in this high symmetry plane.
Yes.
Then suppose they are compatible in this way.
Right.
But are you sure that there's no further obstruction in the plane?
No, that we are not sure. That's
I
why
see.
these conditions which are necessary but not sufficient. So they're necessary if you get an insulator, but they are not sufficient to really give you an insulator.
I see.
So if you can't even satisfy this, then there's no hope that you can be insulated.
Right.
But just satisfying this doesn't mean that you must be insulated. So instead, there are cases that you just cannot be really get to that insulator. So those are slightly more topological. Yeah.
And try to confirm. So those n are really irreducible representation at each special k point, which have different group.
Right.
Okay.
Right. So
But however, the conditions are obtained by the smaller symmetry which along the line which connecting two points.
right.
I see. If this is on the line, there is no additional symmetry, you don't get any condition.
Right. Except for the filling, which is the number of bands.
Oh
So just say I have 5 bands filled here, then you cannot have 2 bands filled there. Still be the
I
same.
see. I see. So I may try to find the line which have a highest symmetry, so that to get the more condition.
Right. So here I don't give you the recipe of finding all these, but the idea is that these there are finitely many such points anyway. So these are some finite things that you can check. Yes.
Can you say anything about the nature of the gap closing? If you know that it must occur?
That depends a little bit on the setting, or that will actually require some extra analysis. So for things like that, if you should know the closing is due to a mismatch of the mirror eigenvalues, then you can basically analyze the crossing here, and this crossing will have some KLP or effective linear description usually. So you just say, oh, this is my mirror representation here, and then how does that constrain the Hamiltonian here when it's generated? Then you can say whether it's linear or not. So stuff like that can be done, but it's not as systematic as this, even though it's very straightforward or very standard within this context. So yeah, I try to develop something like that, just didn't have the energy to publish anything about that. But these are something you can imagine doing. Okay, are we all good? So let me just try to recap the punchline, which is to say you really do exactly the same order analysis, but because of these more topological perspective, you realize you should only do counting instead of worrying about the ordering as in the old days. Then when you only have countings, you only have some integers. And very nicely, the conditions, the symmetry conditions between different points, they are just some linear equations. So you just have some collection of integers that's subjected to some linear equations, and you ask if it is a solution or not. If it's not even a solution, then there's no hope that you get an insulator. If it is actually a solution, then there may be other cases, so those will be what we look at. Yeah.
Do you have information which band is a field, which band is not field? So my question is that those n just list number of irreducible rotation.
Right.
But do you also need to specify which irreducible rotation is a field, which one is not field?
Right. So
That seems another data.
So here I keep only those that are field.
Okay,
So the
I
example is that here maybe I have many representations, but
Okay.
in my counting I have delta 3 equals to 0 because it's here but it's not field.
Oh, I see. You're only counting the one which
Right.
is field.
You only count the ones that are field.
But do you get the equation which for one is empty? Or these two equations are the same?
Well, if you do get an insulator, and this is like a type binding model,
Yeah.
then you know that the other set has to be basically also compatible with a gap.
Okay.
It's like a complementary of that.
So
So
the counting field is enough.
just counting field is enough because in practice, if you do any more realistic calculations, there's infinitely many states above your Fermi energy. There's literally a continuum out there. So saying that bands that are not field is not very sharply defined concept. Okay, so all we know, or the main conclusion is just that this problem is reduced to a very simple one about linear equations. And linear equation is really almost the simplest mathematical structure you can get out of anything. So we basically want to ask, what are the set of integers here that will satisfy my set of equations? So the solution space to a set of linear equation is a vector space. That's basically what this is, except that its integer value is not exactly vector, but those details are not very important. So for practical purposes, we just think of the solution space as a vector space. Then you can start talking about the addition of bands, or maybe just say some field bands and some other field bands, and you will just add them. And that's also going to give you a solution. So I should write it here. So let me try to say that in a slightly more precise manner. I start with some n, which is a collection of field irreps, just a set of counting. So I have a collection of integers, and I have some numbers of them. So for every high symmetry momentum, if I have 3 representations, then I get 3 from there, 2 from there, so on and so forth. But this is a finite number. So I start with some collection of integers, which is d of them. And now I want to subject it to some linear equation. I want to make sure I actually have something which is a solution to it. Then I have some c, and I want to know that this is 0. So I want to find the subgroup of this for which this is true. So without going into the details, let me just call them band structures. So let me just define band structure as the collection of n such that this is true. Then this has to be a subgroup of this one, and any subgroup of C to D is some C to D. So this will be some C to some other integers. So that's basically the structure we tease out of all these discussions. Instead of thinking about all these combinatorics of how they may be connected, if you really want to know what are the ways to get any set of isolated bands, then you will just look at the solution space, which in this problem is some C to some power. So it's like a finitely generated invariant group in particular, and it's free and whatever you want to call it. So it's just the analog of a vector space in this setting of integers. Okay, So this is really the solution if you like. But there are two caveats. So first, note that we've talked about integers. That's how we really get the group here. So that would mean that these n's may have negative values. But if you really think about it in this language, in which I just do some counting, then the smallest number you can get will be 0. So by saying I have this group of integers, then I'm really extending my definition of what it means to be a band structure. I'm even allowing for the filling of a negative number of bands, basically. So that you can say is topological, or if you want to think about it in relative topology, that is fine. But however you want to think about it, you just need to remind yourself, if you look at a solution and has negative numbers, then you really cannot interpret it directly as a set of field bands. It may be the relative difference between two sets of bands, that's fine. Or you can just say these are non-physical solution and don't worry about it. That's also one possible perspective. Or maybe for John, like you will think of it as having positrons. So that is also fine. So it's really a matter of interpretation. So that's not a really big problem. We just need to.
Yeah, but the negative one probably can always be fixed, right? By adding some trivial band. That's the question. Whether even suppose you find a solution with a negative integer.
Right.
But that's actually correspond to existing case by you can make any negative solution positive. That's my question.
That is fine. Yes, that is fine. Okay. So these are just part of the theory, I would say, or part of the structure. It depends on how you want to interpret it. So that's one possible interpretation. Any negative solution, you can add with some positive solution, it will be positive after all. So that's fine. So that's one caveat. The second caveat, which is more important, is that I've used the word band structures here instead of calling them band insulators. So that's really important because it's known that these may not be band insulators, in fact. So of course you can have trivial failure of that. Let's say if as a function of k, you have some bands, there's a continuous gap, but then they disperse in such a way that your Fermi level is actually here. Then you don't get an insulator, but it's like a trivial version of it failing. So let's not worry about it, but you can actually have more non-trivial cases. Let me explain how. So remember, we've been solving all these symmetry constraints. And in order to even talk about these numbers, it's important that you first look at some point in which you have some symmetry to start with. So all these constraints, they only tell you if there must be some crossing along high symmetry line. Let's say something like that. But if you imagine having a vial semi-metal, so this is real semi. And let's say I have inversion symmetry, so I have inversion. And we know that inversion symmetry is only going to tell you they only have representations at the 8 high symmetry or the time reversal momentum, just the corners. So if you think about the representations of inversion, it's just some parity, P0, P1, so on and so forth, at these 8 corners. And they don't really have any relations between these two, because going from here to there, there's no symmetry left to. You don't have inversion. So in this language, you have a trivial problem. There's no condition to solve. So you just say the only condition is the number of field bands, and you can have any versions of these inversion eigenvalues, and it's fine. But it's known from some pretty old paper, I guess maybe 1 decade. So Ashwin and Murray and collaborators, so they knew that it's not exactly true. If you just have inversion and inversion symmetry and no time reversal, for some distribution of parity eigenvalues, you actually get a vowel point, which must be there because of the parity eigenvalues, but you don't really know where that is. So this is just to say you can have some apparently insulating solution to the band structures, which is just having gap at all these points and there's no extra conditions. But in fact, that can be more subtle because you can have topological degeneracies in the interior of the PSO. And this I cannot quite detect using that method because this is not really due to some symmetry eigenvalues that are crossing. It's just some topological degeneracies that are stable locally.
And in particular, this closing can be below the Fermiology?
Well, that is encoded in the parity. So So one example is really like the TI case. Let's say I give you one band which is filled. So I know that my field length is 1. Maybe my parity is positive everywhere, except for this one which is negative. So I can tell you I have one band. I look at the parity eigenvalues at all the high symmetry momentum. There's a gap there. It's well defined. I have all the parity numbers. Then it turns out that this -1 would mean that there must be a file point connecting your one band to the band above it. So if you're saying, oh, my field length is actually 2, then that's a different story. So if you have actually 2 negative and positive, then this file point will be now below infinite surface. But that much is known if you actually know the high symmetry point. So what is important is that we should acknowledge the fact that this description, which just solves some linear equation, it is a necessary condition for getting insulated, but it's not sufficient. So there will be cases for which you can never get insulators due to some distribution of such symmetry eigenvalues. But those are more subtle, and it's still an open problem, even though we know certain cases where they can appear or not. So, okay, so these are the caveats, but if we are good with that, then in the last 20 minutes or so, let me try to talk about this other perspective. So, I hope it's useful. So far we've been talking about band theory in the canonical context, which is that you think about momentum space, you have Brillouin zone, and then we talk about how the bands can be connected and so on and so forth. But if all we really care is whether you get some band structures or maybe even band insulators, that's actually a kind of a shortcut to get some of the answers. So that would be going to real space. So I like to call this real space or high school insulators. So let me try to recap what we learned in high school chemistry. So in high school chemistry, we were taught that there are only 3 types of bonds, which are ionic, covalent, and metallic. So it's suggested that this is metallic, and these are supposed to be insulating. So let me really draw what they are as in like a high school chemistry fashion. So in an ionic crystal, the atoms are arranged nicely, but then they have some charge on it. So something like this. So the atoms are arranged in some nice crystalline manner, but then they have some extra charges or some quantum less electrons, something like that. So that's an ionic crystal, and we know this is insulating because the electrons are all sitting here, for instance. So this is an example of the sodium chloride, for instance. And maybe I can have covalent solids, which could be, say, diamond. So this is the ugliest diamond you'll ever see in your life, I think. And the point is just that the carbon, they are connected to each other by sharing electrons in some interorbital or interatomic space. So they're really sharing electrons, and you still know where the electrons are. So they sit here. They sit between the atoms. But anyhow, they sit somewhere. So metallic in the high school picture, you just have some electrons that are flying, something like that. So this is metal, let's not worry about it. But in this high school chemistry perspective, you really think these are the only insulators we get in life, kind of. So there's one common ingredient, which is that you know where the electrons are. So in this perspective, you get an insulator precisely when your electrons are localized to somewhere well defined in space. So it may be localized to the atoms, or it may be localized to the bonds, but anyhow you know where they are. And because of that, you get an insulator. But now we can take a more quantum perspective on all these and say what that means. So for the ionic crystal, I can imagine it, say a 1D example. I can draw it as some series of potential. And this is really trapping my electron. And this is losing one electron. So this will be the anion, this is the cation, for instance, something like that. But if you look at this, this is insulating, but you could as well get an insulator if the electrons are classical particles. Let's say if these are really marbles and you just have some potential well, and they just sit there, it's true that you have gapless excitation, you can move a bit, but you still don't get any conduction of these marbles. So I would say this is more or less like a classical insulator. You don't really need the fact that your electrons are quantum mechanical. And that's a very distinct perspective compared to band theory, in which everything is starting with a plane wave and you ask how they interfere, so on and so forth. So we can try to reconcile the two pictures. And by saying this is like a classical insulator, all I mean is that there's no essential degree of quantum entanglement. So more precisely, let's say I have my 2D sample. And maybe these are my sites. And maybe my electrons are localized to these spots. So now we can try to write down the ground state wave function for this insulator. And it will be just saying I take my vacuum and I try to occupy these states. So maybe they're at origin 2, 0, 1, 1, so on and so forth. So just start with the vacuum and I just create some electrons. They're all localized at these states. Then I get an insulator. In particular, you can imagine doing an entanglement cut. So I can say, let me cut away this region. Then you can rewrite the state as just saying you have the vacuum inside. So if I do an entanglement cut, you can cut away any region you like. Then it's just to say you rewrite your state as what is inside and what is outside. And with respect to this cut, you don't get any quantum entanglement. So that's the sense in which these are classical insulators, which is to say there's a limit in which you just don't get any quantum entanglement. But of course, we know in reality these are never that well localized. So they're not really delta function localized, for instance. So if I look at the wave function here, it actually is something like this. So maybe if I look at this line, the wave functions are like this. Then if I really look at an entanglement cut here, you do cut across the wave function, then you can get some entanglement out of it. But the point is that respecting all the symmetries as well as just the symmetries here. So respect all the symmetries and still want the same insulator more or less. I can deform my system into a version in which the wave functions are just much more well localized. Then I can basically get rid of all the quantum entanglement. So these are boring types of insulators in the sense that you can get rid of all the quantum entanglements in some smooth manner. So these we'll call atomic insulators, or real space insulators, or high school insulators. And this is basically a picture for both ionic and covalent solids. So we can imagine that this is still some solution to the band theory problem, or the band symmetry problem. In the sense that if I give you such an insulator, you can imagine going to Fourier space and you will still solve the equations we've written down. So this is a particular simple set of solutions, but they're actually quite useful even though they're trivial in terms of their properties. So to see why they are particularly easy to find or to discuss, we can again work out one example, which is again going to be graphene, but let me just do it step by step. So let's say I start by telling you these are my lattice patches, then I can draw my green cell. So my rule is now that I know I have an insulator, which is of this trivial or atomic type. and it's generated by saying I have one electron localized at this spot. So now I also know I have some symmetries in the system. So I've told you this is going to be graphene. So we again keep the mirror and also C3 rotation. So if I keep the mirror, then by localizing an electron here, I must also localize an electron here in order to get such an insulator and respect the symmetries. And these are just lattice translations, right? So they will also be localized here. And now we also have a threefold rotation, but with a little bit of imagination, this is going to be threefold related. So we know that this is, again, giving you just a not very ideal honeycomb lattice. So this exercise is telling you that if I start by only thinking about these kind of real space insulators, I only need to tell you the positions of a subset of the electrons. Knowing just that, then the rest will be generated by symmetries. So this is the first point, which is that these are quite readily, can be quite readily tabulated, because you just need to know the positions of them and also how to represent the local symmetries here. But then if I look at this insulator, let's say this is the standard graphene example, we immediately know that if we look at the band structure, so this real space, I can go to K space. Then this will have this standard graphene dispersion, something like this. So in particular, this graphene dispersion, if you now do the counting of representations and so on and so forth, they still have to satisfy those kind of unit equations. So we're really good here. So the main claim of that discussion is the following. If I want to think about only a real space insulator, I don't need to worry too much about all these stuff of the representations in the momentum space and how they're compatible. All I need to know will be two pieces of data first. The lattice in real space. So example would say honeycomb. And then I also need to know the orbitals, which are really the irrep of the point group at that point. So one example we gave that is when you have honeycomb and then you have the example C3 being +1. Then we know these two together is going to give you this band structure of a 0.k. But you can imagine now changing the ingredients. You may not start with this lattice, you may not start with this orbital. For instance, you can take the same honeycomb lattice, but maybe under C2 representation, I have the two representations, which is like a p wave, or px plus ipy kind of orbital. So let's say I also have time reversal, so these are degenerate. Then you start with 2 sites and 2 orbitals per site, and you have 4 bands. And just knowing these data is sufficient to tell you that in momentum space it has to look like that. So just telling you real space data, the lattice and the orbital, then you can go to momentum space, and this step is nothing but Fourier transform. So I can do a Fourier transform, then I know all the representation content, which are fully fixed by these data. In particular, this is still a solution. So if I look at the counting here, this will give me some n. So this n will have to satisfy this equation. Just because I start with some insulators, so there's no way that you will have any crossing up above that. So now we've basically tried to connect this real space picture to the momentum space picture in which you talk about representations and solutions. And this is just a Fourier transform. And in particular, you can imagine doing a systematic study of all the lattices and all the orbitals. So all the lattices have been classified under what is called Wyckoff positions, but you can imagine it's a doable problem. You just talk about all possible spatial symmetry groups and you talk about all the possible distinct lattices. And at every point you have some orbitals, which are some irrep of some finite group, so they are doable and have been done. So now you just take a collection of all these, and that would define what we call atomic symmetry. And under Fourier transform, we get some n, or let me call that a, which satisfies this equation. So under Fourier transform, we just get these, which will have to be solutions of linear equations. And that would mean this group of atomic insulators is going to be a subgroup of band structures. So all I've been trying to say is that analyzing the real space problem, which is simpler and have more or less been done because all these have been classified 100 years ago, we can find a particular subgroup of band structures or a particular solution, and we call this some C to integer deviance. Then you just have a subgroup of this, so it's again going to be some finitely generated free group. So now the surprising point is that from that discussion, all we know is the following. The group AI will have to be again some C to some power. So just because it's a subgroup of that, and it's so very naturally you want to compare these two numbers. So you want to ask if it's a subgroup, if it's really basically almost an entire group or not. And the claim is that these two are the same number. Always, for all magnetic space groups. So this is kind of what we, or kind of the main result of those two works. So that will be, what's that word? So that's basically what we established. So just taking at this discussion, it may not be very meaningful to you because I'm just saying, oh, there's some groups and they have the same dimensionality. That's it. But if you really think about it, that's actually telling you a little bit more, because the fact that they have the same dimension would mean that you can basically find a full set of generators for the band structures using only your data about the atomic insulators. So the more precisely is saying if you know all the generators here, then you can try to form some linear combination with fractional coefficients, then you can generate all the other possible band structures. So I've started by telling you that, oh, you should think about it in the old manner of band theory. You talk about bands and representations, how they may be connected. There's some non-trivial connectivity or compatibility relations between them. But at the end of the day, with this result, it's telling you that you don't need to really worry about it. If you want to find something that satisfies all the symmetry constraints, all you need to know will be the real space solutions, which have no quantum entanglements, particularly trivial. But as long as you know that, then you can know all the possible band structure solutions. So that's really the power of this equation.
This is really surprising because you mentioned that some solution band structure must have a gaseous point somewhere.
Right.
You know? And looks like those solutions can never be atomic insulator. And so that means these two are not equal because this exception.
Right. So that's the point which is not clear yet in the way I described it. So I've only told you they have the same dimensionality, but I didn't say that they are the same group. So if they're really the same group, so if this is strict equality, then the case you described would be an exception.
Oh, I see.
But in fact, it's still a subgroup. So there are cases in which it's a strict
They have same
subgroup.
dimensionality, but
Right.
not the.
Exactly. So that's the second part, which is the interesting part.
I see.
So in the first part, I just told you that if you want to think about solutions to this compatibility relations, it's good enough if you know all the atomic insulators. But I haven't quite told you how to really find the solutions. And the second part is to compute the quotient, basically. So I have some group which is a subgroup of something else, and you want to understand the structure of how it's a subgroup of that, so you just look at the quotient. So you just define this as the quotient, and it's going to be some finite abelian group. because of this. So it's always a finite, always all portions. So now this may not be trivial. So you can have cases in which you say C, 2 crowds, 3 copies of that cross C4, and so on and so forth. So what does this mean? So this would mean that if I look at some atomic insulator and I try to evaluate this particular index, then because it's really what I quotient out, so that has to be 0 if this is atomic. But now if I just give you some general band structure, then it may give you some answer which is not 0. Maybe it's some, say in this group here, maybe it's 0, 0, 0, 1, something like that. So that would imply this is the solution to all the compatibility relations, so it can be gapped, or at least along all the high symmetry lines is going to be gapped. But then you can never interpret this one as any atomic insulator just because it's a non-trivial class in this portion. So if I give you any material, I can just compute the representations that I will get this B or maybe N. Then I will just evaluate this particular index. If you find it to be non-trivial, then you know for sure the material you have has to be topological in some way. At least there's no hope that it can be an atomic insulator. So now how exactly is this non-trivial will depend on the symmetry setting. So for instance, if you have this example of the vowel points due to parity eigenvalue, then you evaluate this, you will find that it's actually non-trivial. But it doesn't mean it's an insulator. It actually means that the entire class of these band structures will have that same number of vowel points, or stable vowel points. But if you look at some other settings, we can prove further that these are all insulators, that these are all compatible insulators. And these will just be some topological insulators. And the merit of all this discussion is that it's reduced to some simple linear algebra. So all this can be done very readily. And in particular, we've computed for all kinetic space groups. We know all the answers of this quotient. And they can even be applied to materials. So in some recent works, so this is the last reference here, that we've been doing with Nanjing group in China. We basically try to say you use this methodology, you apply it to the 230 space groups for materials without magnetic order. So that's class A2. And actually, I should write it here. That will be the end. So for class A2, so this is and spin orbit. So you can use this methodology and you just do some initial calculation. Then you can find this vector n. Then you can have 3 cases. So you start with material. And then you do symmetry analysis. Then you set from n. Then you have some 3 cases. The first is that n is not even a solution. So or Cn is not 0. And this must be semi-metal or metal. So in particular, you can find cases in which it's Dirac semi-metal, if you like, or maybe you have nodal lines and stuff like that. The second case is that n is in yes, but the n is not in the subgroup of atomic solutions. Or basically, you can compute this XBS of n, and it's non-trivial. Then for this class A2, then we know in particular that it's actually insulated. So it's some topological crystalline maybe insulator. And the third case is when it's not only a solution to the band structures, but also an atomic solution. So that is the same as saying SBS is trivial. And this is maybe or could be atomic. So it's actually slightly more subtle because even in this case, maybe you still have band topology. It's just that you cannot detect it using this method because you only look at representations. So this is the case of materials for which they may be interesting, but then a fairly good fraction of them will be trivial anyway. So if you look at any material, you just do this analysis of finding the representations and then compare it to 3 cases. Then the most interesting cases will be these 2. Because in the first case, you just get some topological semimetals, if the energetics are right. In the second case, you get some topological crystalline insulators, or just topological insulators. And this Nanjing group, Xiang'an and his student, they basically use this method and they look at some database. There's some 18,000 possible candidates, and you just go through these. Then you can easily find thousands of topological crystalline insulators. But among them, maybe many of them don't have good energetics. So if you do some additional filtering, you get still hundreds of them. So I think the merit of all these methods is that it's really simple enough that you can integrate extremely readily into some ab initio packages or ab initio methods. And that's how they found all these new examples of materials which are topologically interesting. And I will end by saying there's also some contemporary work, one by IOP Chen. So that's Chen Fang's group. And also from Princeton, Mobile. So these are contemporary and they do very similar analysis and they find roughly the same number of topological materials. So if you look at their method, the narration may be slightly different, but I would say these are all the same thing, up to 0th order at least. So I guess I'll end here. And just to try to convince you that this is actually a pretty efficient way to understand band theory or band topology, and in particular they can lead to really materials prediction in some easy manner. Thanks.
Questions?
So I think you said before that there could be ends which are in BS, but then they still have a gap what's required to have gap points, like for vinyl semi-metal, is that right?
Yes.
So that's kind of not in this.
Not in class A2. So class A2, we know there's no such cases.
Okay.
Right, because the example we gave is in class A. So in fact, without time reversal symmetries, then you start getting vowel points, right? More easily. Because if you have time reversal symmetry and also inversion symmetry, then you just don't get any vowel points.
So how do you know that you never have any such thing?
Right, we don't have a very systematic answer to that. But what we know for sure is that for class A2, is all like that. So these are all insulated. For class A1 is the other case around. For class A1, so the switch off spin-off coupling. All these XPS or trivial things, they're actually semi-metals. So the next case of some magnetic symmetry is not A1 or H, some really magnetic setting. That one is more subtle. We know examples of both cases. We haven't mapped out exactly how or which setting if you want. So we know only isolated cases for the most general magnetic setting.
So you also mentioned that in the third case, even if it satisfies the atomic insulator condition, it can still be topological in some way.
Could be, right. So one example is say, let's say class A2. Let's say I have this space group of only translation, nothing else. So if that is the case, you still have the C2 topological indices, right? Strong and weak indices. So in that case, you still have some topological band structures, but this method is reliant on the representations. So if you only have transition, there's nothing I can detect. So the story is that even if you really apply this method to that particular space group, case 1 is interesting because it will still be, well, it's actually not that interesting, just some simple metal. But then case 2 will never happen. Case 3 doesn't really mean that much because it can be topological, which is no problem. So if anyone tells you they can find a full classification using only symmetry data, you should take that claim with some pinch of salt. Some people do claim that, but that cannot be true.
Actually, I have a question. So I think this method can also be applied to some on-site symmetry, like together with space group symmetry, right?
Right, yes.
Yeah, and the reason why I think about that is I'm wondering whether there's some like a dimension reduction structure, in this result.
Right.
Of course, the example you were talking about are mainly maybe 3-dimensional, but we know, I think, at least for many topological crystalline states,
Right.
you can understand it by some high symmetry plane or high symmetry line decorated by some
Right.
some lower dimension object, topological object. So I'm wondering whether there's something similar.
Yeah. So it's intertwined with all these, but I shouldn't say we understand the gene structure. But this is quite interesting. So in fact, if you look at only inversion and translations and class A2 and then if you compute this one, then you have, so it's 3x. It's C2 cubed. These are just the weak C2 indices. But what is interesting is that we have the C4 here. So instead of C2, if it's strong Ti, then you expect C2. So that would mean that if you look at the full king parity criterion, you actually don't get the full data about the topologically non-trivial band structures. So we look at this, we know that the 0 is trivial, 1 is the strong Ti, 2 is something topological, 3 is again a strong Ti. So that we know. But 2, we thought is something which is topological, but we don't know what is the signature. But as it turns out, this is what is now called higher order Ti. So in fact, if you really think about it, this 2 is like 2 copies of strong Ti. And if you look at it from real space, you can understand this 2 from saying you have quantum spin Hall. And you arrange it such that you have, in every unit cell, you have 2 quantum spin Hall, which are parallel to each other. So if you have only one, so this is one unit cell. So if only one quantum spin Hall is a weak Ti. Now you have 2 quantum spin Hall, then it's not going to be a weak Ti. You also don't have a strong index when you start something weak, kind of. But these are pinned in space because there's an inversion center, and this is say maybe 0 and 1/2. So it's true that you have these quantum spin Hall that are pinned to that plane and you cannot quite move it. So as it turns out, this is really an interpretation of this 2. And if you look at an inversion symmetric surface or termination, then you'll start getting these 1D quantum spin Hall hash modes. So there's a connection. It's like whatever we have extra here that cannot be interpreted as some intrinsic 3D phase. It seems that they are some lower dimensional things that stack in some spatial symmetry curve. So we know that is true for A2, but we haven't quite understood the magnetic cases.
One more question.
You have a result that dimension of the atomic insulator is same as the dimension of the band insulator. That's a proof or it's a check for all the cases?
We basically check it for the 230 space groups, the pure space group with the time reversal, and the rest you can prove. So it's like a mix of both. So it would be nice if we have more general proof. But we could only check it for the pure space group case. There's some physical intuition why that's probably true, but we don't know how exactly to prove it. But starting with that, then we can prove all the other cases.
But there are some topological insulator which is classed by Z. So that seems for those things these two have different dimension.
Right. So those are, for instance, China numbers. So they either are completely missed by symmetry analysis, and it's just some additional factors that are not even entering in this discussion.
I see. So
or you can have some detection of China number modulo n. If you have a 3-fold rotation symmetry, detect that by modulo 3, then that China number will appear in this discussion as a C3 group.
I see. I see. So here it says that for those protected by some kind of crystalline symmetry, it's always it cannot be Z, always some kind of Z.
Well, you can mirror China numbers, for
I
instance.
see.
So that's still C and it's protected by mirror. So it's more the statement that anything we can detect here, if it's a C classification in the actual K-theory sense, we will only detect some quotient of that, like modulo something.
Oh, I see.
Or you maybe the module, maybe the quotient is trivial, you just don't detect anything.
I see.
The best you can do is detect the modulo some integer.
Okay.
So maybe it's a good time to wrap up. Let's thank Adrian again.